So we know sample size greatly affects how sure we are in something. I mean, if you only ask two people something, you can't be very sure that everyone is going to feel the same way as those two people. However, if you ask 1,000 people, then you can start to say, a lot of my population is being reflected in my sample. So sample size plays a big part. We want to be able to have a large sample size, large enough to say what we need, but small enough so that we're not spending all of our time finding out what's going on. So here's an example, quick example of a confidence interval. When you've got 109 students, we need to use a t here just because we don't know the population standard deviation. As you can see, the only point I mean, you can look at the confidence interval notes for this, but the point that I want to bring out here is that the sample size plays a big feature in the standard error or the standard deviation of the sampling distribution. Okay, so here, what sample size should we use? And that's what I'm trying to say here. We know that a particular condition that the central limit theorem has is that n should be large as possible. I mean, definitely the larger the better. We said that it starts doing a pretty good job when n is greater than or equal to 25. In fact, when n is greater than 30, then the average really is starting to become from the normal the normal distribution can really talk about the average. We might not even have to use the t distribution. But anyways, when we are selecting the sample size, in this course we are just going to pretend that we know sigma for when we do this. Basically, I'm going to take this formula that we've always known and rearrange everything to solve for n instead of solving for z or instead of solving for mu. Currently, we've been using this formula. Originally, we just solved for the z-score. When we were doing confidence intervals, we were solving for mu. Now we're going to rearrange it and solve for n. And what we get is that n should be larger than or equal to the z value squared, the sigma value squared, and this thing, x minus mu, which we're going to call the error. So x bar minus mu is just the error, and we're going to square it. So here, just rearranging this formula in terms of n. Okay, and this is what we get. Okay, so here's an example. A university administrator wants to take a sampling, and they know about what confidence they want. They want 90% confidence in their findings. They want their error to not be more than 0.25. Here they're talking about years, so they don't want their error to be bigger than 0.25. This is E. This is confidence. And here, then, they know apparently that the variance, in this case, sigma squared, they know the population variance, which is 2. Okay, so here sigma squared is 2, which means sigma, or the standard deviation, is root 2. Okay, so you have to be careful when using this formula. So n is larger than or equal to some z value. Again, we want to be 90% confident. So what should that z value be? Okay, it's given away here, but here we want to be 90% sure, so 90.9 is in the middle, which means that we have 10% to share on both sides. Divided in 2, you get 5% on both sides. What should the z value be? Again, you can go to your z table, look up 0.05, and you'll find it in the negative 1.6 row, and somewhere in between 0.04 and 0.05. You won't find it perfectly. So I'm just going to split the difference and say this is 1.645, somewhere right in the middle here. So that is the z value that corresponds to 90% confidence. Sigma squared is just root 2 squared, otherwise known as 2. Divided by the amount of error that we're allowing, which is 0.25 squared. Okay, so when you calculate this, then you get 86.59. In this case, you would round up, but in any case, you would round up because 86 samples is not enough. 87 samples will be a little bit more than enough. So when you're talking about n sample size, you always round up. Even if this was 86.02, you would say I need to have 87 samples, at least 87 samples. Okay, so there's our first try at it. Okay, so let's refer back to an example that we had before. Apparently the sample standard deviation was found to be this. suppose we wanted to estimate an error an error of within 0.2 units. Okay, and we want to be 95% certain. Okay, so here we want to be 95% certain. It means there's 2.5% error to share on both sides. We've seen previously many times that the Z value, okay, here's the formula, the Z value is going to be 1.96. Again, it doesn't matter if you choose negative 1.96 or positive 1.96. As you can see, it's being squared. Whether you use the negative or positive, it doesn't matter. Okay, so it's just being squared. Here we're going to use, in this particular case, because we're talking about sample size and just making an estimate, we're going to just use, pretend that S is actually close enough to sigma to call it sigma. So here we will say that S squared estimates sigma squared. Okay, so here is S. We will assume that it's similar to sigma. And then here the error, we want to be within 0.2 units. So this is 1.96 squared times 0.453 squared divided by the error 0.2 squared. Okay, when we do all of this, then I get that n should be at least 19.7. Again, we always round up. Even if it was 19.1, we would still round up that n should be at least 20. Okay. Let's move on then. Instead, if you're talking about a proportion, so here we've been talking about estimating numeric data. If you're estimating categoric data, there's a few more wrinkles. Okay, so the formula again is just the typical Z formula for sigma rearranged to solve for n. Now, here's something that you're going to possibly be stumped on, so pay attention. When you don't know anything about p, so let's just say we have no idea what p could be, then you can just sub in that p is 0.5. It is the worst case scenario. Okay, if p is equal to 0.5, it's the worst case scenario. So here, notice here I've got p times 1 minus p in the formula. Here then, if you graphed the plot x times 1 minus x, or p times 1 minus p, also simplifies to this, you will find that in between 0 and 1, which is, proportion always has to be in between 0 and 1. You'll see that the highest point, the worst case scenario, is 0.5. So if you know nothing about the situation, you just want to know how many sample sizes, or what sample size will be enough, you can, if you have no other information, use p is 0.5. Okay, so here's the formula. Still the z squared, still the e squared. Here, though, instead of having sigma squared, we've got p times 1 minus p. So this is not squared, it's just p times 1 minus p. So n is larger than this. Okay, so here's the situation. Suppose we wanted to estimate the proportion of Canadians who will shop in the United States on Black Friday. That just happened a few days ago. We wish to estimate the value of p within 3 percentage points. So this is the error, within 3 percentage points. We want to be 95% confident in this. Okay, so we want to be 95% confident. Of course, Z, you're starting to get very used to this particular number. 0.95 is in the middle. That means 2.5% is on the side. And we've seen many times this Z value is 1.96. Okay, if we use the negative and squared, it's going to be the same thing as a positive and squared. So here's the Z squared. We don't know anything about, so no prior information is known about p. Worst case scenario is that p is equal to 0.5. So this would be 0.5 times 1 minus 0.5, which is also 0.5. Be careful when you're talking about the error. This is not 3 squared, but 3%. So this is 0.03 squared. When I complete that calculation, I get 1067.1. Okay, again, here it doesn't matter that this is low. I'm always going to round up. So this will be 1068. At least 1068 samples need to be taken. As you can see, when you're talking about proportions, you need to be a lot more. You need to have a lot more information. Remember that to use the central limit theorem, we had that requirement. You needed at least 10 successes and at least 10 failures. So at bare minimum, you need 20 samples, and that is if you get exactly 10 and exactly 10. If one of the if the success is harder to come by, and out of every 20 you've only got 1, then you're going to need a lot larger sample size. Okay, so suppose we took a small little sample of just 10, just to get an idea of what P could be. So out of 10 Canadians, 2. Okay, so now instead of saying that P is actually 0.5 because we had no information, maybe now we'll say, well, it doesn't look like P is 0.5, which is the worst case. Maybe P hat is going to be 0.2. Okay, so 2 out of 10 said they were going down to the States. Fine. Here then, how does our formula change? Well, we still have the exact same z squared. We still have the exact same error squared. But here, instead of 0.5 times 1 minus 0.5, we've got 0.2 times 1 minus 0.2. As you can see, this actually greatly changes the sample size. We're not having the worst case scenario here. Okay, so here then when we calculate this, n should be at least 682.5. Again, 682 is not enough. 683 is the next value. So I need at least 683. One small caveat that I noticed while I was messing around on Minitab is there's a way to calculate this on Minitab, but it doesn't use this method for proportion, so I'm not going to show you that. But it can use this method for averages. So it only works for averages. It might not be even worth showing to you, but seeing as I'm just making a video, I'll do it anyways. Okay, so here I'm going to recreate this example using Minitab. When you go to Stat, Power, and Sample Size, I'm going to use Sample Size for estimation. Okay, so here I've already practiced this question a little bit. I'm looking for the mean, which is based on the normal. There is the option here for proportion, but see, it's not based on normal, it's based on binomial. So it's a different method. It's not going to give you the same calculations that I will expect from you. So it's not even worth going into. Okay, so here I'm trying to estimate the mean. What is the standard deviation? In this particular question, the standard deviation here was 0.453. Okay, so here it is in the formula, 0.453. 0.453. And I want to estimate the sample size. What is the margin of error? Okay, so what is E? In this question, it said that I wanted to be within 0.2 units, 0.2. So there's 0.2. Make sure you have a look at options. You want to make sure your confidence interval, confidence is whatever level you want it to be, 90, 95. You want it two-tailed. And you want to make sure that you're checking off this box if you want to have Minitab do the same calculation. We need to assume the population standard deviation is known. Then, of course, you get the sample size that we also calculated. Here we said 19.7, which always rounds up to 20. Minitab does the rounding up as well. We've got 20.